Good afternoon, my fabulous chemistry students. Today, video number 5, the alternate acid and base theory. This alternate acid-base theory arose because there were some exceptions to the normal acid-base theory. It just didn't really work there, and ammonia is a great example. The other one is on the list of acids, and it's called an organic acid. You'll hear me refer to them as COO, because they end in COOH. Okay, so these two species have made it so we need to come up with another theory of acids and bases. Why do these things work like acids and bases when they don't fit the normal explanation? And the name of the alternate acid and base theory is called the Bronsted-Lowry theory. And now we will encompass all of them. So that acid-base theory, alternate acid-base theory, otherwise known as Bronsted-Lowry theory, explains specifically the behavior of weak acids and weak bases. Now, I remember in the last notes or 2 notes ago, I talked about the difference between a strong acid and a strong base. So remember, a strong acid, if it's strong, it dissociates 100%. A weak acid is going to dissociate, let's say, 70%. So some of that original molecule will be present in the liquid, and that's why they act a little bit differently. So Bronsted-Lowry's acids are what's called the proton donors. So that's what the major change. It said instead of producing H plus ions in solution, now we changed it to that Bronsted-Lowry acids donate these H pluses. Okay, and here's a little pictogram where HCl is an acid. It gets put into water and dissociates. The H plus leaves the Cl here, goes out, and then it hooks up with the H2O to make this hydronium ion. Remember, we discussed this before. H3O plus is synonymous with H plus. They work the same way. So I've now made H pluses in solution. HCl donated that H plus. The bases become the proton acceptors. So now the Bronsted-Lowry bases accept that H. And here's that ammonia. And this is how this works. So H2O becomes, when one of these H's leaves, it's going to go on to here. And that's that coordinate covalent bond. Let me redraw this because I want it to be right. Technology will work for me. If I lose an H plus, remember that's a proton now. There's no electrons. But hydrogen still wants 2. And these lone electrons is where that hydrogen is going to bond to form this ammonium ion. And when I bond with no electron sharing, this H plus hooks onto a lone pair like that. Remember, we call that coordinate covalent. It seems to creep into the test every year, and this is the most common example of a coordinate covalent. So now, this NH3 ammonia, accepted the proton. It accepted the proton. It became this ammonium ion here, and look what's made. This OH minus, which turns it into a base. So it doesn't actually have an OH in the ammonia itself, but as it reacts in the water to form ammonium ion, now OH is produced, and that's why it becomes a base. Conjugate pairs. So this is something I'm going to go through, but we are not going to really hold you guys to this. We use 2 brackets just like we do our double replacements, except for now it's acids, bases, conjugate acid, conjugate base. Okay. So it says 2 brackets connecting the sides of the reaction represent the acid-base and conjugate pair. Within the pair differs from the other by merely 1 hydrogen. So if I lose a hydrogen with HCl, I become Cl minus. So these 2 are pairs. The water here, H2O has gained the H. So these 2 are conjugate. This is the base with its conjugate acid. This is the acid with its conjugate base. And that's how that works. They're always a pair. There's like an equal and opposite always with this whole acid-base thing. So let's do a few examples with this conjugate acid and base. There are 4. I will do 2 and you will do 2. How about I do number 2 and 4 and you do 1 and 3. So I'm going to HCl. Oh, well, I can't do 2 because I just did 2 on the other. 2's on the other page if you didn't notice. All right, I'll do 1. I'll do 1 and 4. NH3 and HOH. Okay, NH3 gains an H here. And HOH loses an H here. Okay, good. And let's go down. I'm going to do 4. Okay, H2O is going to accept. Okay, so here's the conjugate base, conjugate acid, the acid, the conjugate base, and HNO3 definitions are wrong. HNO3 is going to lose the H here. So this is the acid. This is the conjugate base because by definition, the acid is the proton donor. And then the proton acceptor is here. So this is the base with the conjugate acid. Because H2 becomes the proton donor here, or acceptor. It accepts that H. So that's just how we use those rules. Okay. More chemistry stuff that we just got to make sure that we cover. A substance can act like an acid or a base. Amphoteric. Ambidextrous. I can use my right hand and my left hand. Wonder if I can do something with that to make sure I remember. But water can act like an acid or a base. And here's a reason. I have H2O and H2O. One molecule can accept an H plus. One molecule can donate an H plus. So here I got one H going from here to here. And this becomes H3O, and this becomes OH minus. So water is amphoteric because it can be either one. Okay. Which of these are amphoteric? HBr. No. Br minus. No. HSO3. So do it out. HSO3 goes to H plus SO3. Oh, here we go. How about this? HSO3 plus HSO3 could become H2SO3 plus SO3. So here, one H leaves here. One is an acceptor and one is a donor. Bam, C. All right, anyways, enough of that little stuff. All we need to really do when we do this is that there's an alternate acid-base theory, and now the new definition becomes acids are H plus donors, bases are H plus acceptors, and believe it or not, that theory works with our previous theory of acids and bases, and now it's all-encompassing and helps include the two different the exceptions. So the exception to base is NH3. I wrote HH, so you have to excuse me. NH3, and the exception to the acid on the list is the COO, or the organic acid. And I know that was a little bit long-winded, but I want to make sure we got the theory right. There's only going to be one more long video for this particular unit, and that will be when we start doing the titrations and get ready for the lab. So we are done. I'll see you guys in class tomorrow.